We're launching into the foundational architecture needed to build truly intelligent large language model agents. Today, we're doing a thorough analysis of the white paper, Context Engineering, Sessions, Memory, which lays out the blueprints for making these systems stateful and persistent. For clarity, this deep analysis is generated entirely from the provided source material using artificial intelligence. Our mission for you is straightforward: to understand the sophisticated mechanisms required to transform inherently stateless LLMs into persistent, stateful, and truly personalized assistants. This is really the critical knowledge layer for anyone involved in high-stakes agent development.
To start, we must clearly define the architectural layers guiding this transformation. The entire strategy rests on what's called context engineering. This is the dynamic process of assembling and managing all relevant information within an LLM's context window. It's the fix for that statelessness problem. And this relies on two major components: sessions and memory. A session is the container for the immediate conversation, sort of the agent's real-time working memory. And then memory provides the long-term persistence, consolidating information across many sessions to create that continuous personalized experience.
So context engineering isn't just about writing a great system prompt anymore, is it? It sounds like we've moved well beyond those static instructions of traditional prompt engineering.
We have. It's now about dynamically constructing the entire payload based on the user, their history, and external data.
I like to think of it as a digital mise en place. You're not just giving the chef a recipe, you're ensuring every single ingredient is laid out perfectly before they even start.
That analogy is highly accurate. Context engineering governs three essential categories of components that fill that context window. First, there's context to guide reasoning.
Okay, so this is the agent's core programming.
In a sense, it includes the system instructions for its persona, the tool definitions for what APIs it can call, and few-shot examples to guide its learning in context. The second category is evidential and factual data. This is the substance the agent reasons over.
Things like long-term memory or data pulled from a search.
Exactly. Long-term memory, external knowledge from RAG, and outputs from tools or even other subagents. And finally, there's immediate conversational information. This grounds the agent in the present, the conversation history, a temporary scratchpad for calculations, and of course the user's current prompt.
Managing that flow of information dynamically seems paramount. If the context window gets too cluttered, we run into the problem known as context rot, where the LLM starts to lose track of details.
It does. And this dynamic management leads directly to a four-step continuous operational cycle. This is the heart of the agent's execution loop for every single turn.
So what are those 4 steps?
Step 1 is fetch context. The agent retrieves user memories, RA documents, and the current session history. Step 2, prepare context. Here, the framework assembles the full prompt.
And this is a blocking process.
It is. It's on the hot path, meaning the user waits for this to complete before the agent can even begin to think.
If that preparation is on the hot path for every turn, doesn't that create a significant performance bottleneck? Especially with long histories.
It absolutely creates a latency risk.
Yeah.
That's why managing the session data is so vital, a topic we'll cover shortly. After preparation, step 3 is invoke LLM and tools. The agent thinks and calls functions until it has a response. And the final step, 4, is upload context. New information from that turn is uploaded to persistent storage.
And that upload happens in the background.
Critically, yes. It's designed as an asynchronous background process. The memory consolidation happens without making the user wait for their answer. We want the user to feel speed.
That separation between the hot path preparation and the asynchronous upload seems like a fundamental design choice for scalability. Let's focus now on the session. If memory is the long-term knowledge base, the session is the workbench for a specific conversation.
A very good way to put it. The session is defined by 2 primary components. The first are events. These are the chronological building blocks: user input, agent response, tool calls, and tool outputs. The second component is the state, or the scratchpad.
And this is just for temporary information.
Correct. It holds structured working memory only relevant to the immediate dialogue. For instance, the items in a user's shopping cart right now.
When you bring this kind of architecture into an enterprise environment, security and privacy are obviously non-negotiable. What are the most critical production requirements for managing these sessions?
Security and privacy is number 1. Strict isolation is the cardinal principle, usually enforced through access control lists or ACLs.
So each user's data is completely walled off.
Completely. And a key best practice here is redacting personally identifiable information, PII, before that session data ever gets persisted to storage. This dramatically limits exposure in a breach. Beyond security, you need data integrity, which means a deterministic, chronological sequence of events. And finally, performance is paramount. Since this data lives on that hot path, retrieval must be exceptionally fast.
That need to keep history manageable brings us to the problem of long conversations. Without management, you hit context window limits, API costs soar, latency increases.
And you get that quality degradation we mentioned. It's like a savvy traveler deciding which notes to keep and which to summarize before packing a limited suitcase.
So what are the strategies for that?
We have to actively employ compaction strategies. The simplest is just to keep the last n turns, a basic sliding window. A bit more efficient is token-based truncation, where you count backward from the most recent message to fit within a token limit, say 4,000 tokens. The most complex but often most valuable is recursive summarization.
This is where an LLM summarizes older parts of the conversation.
Precisely. That summary is then prefixed to the recent verbatim messages.
But that summarization step must be computationally expensive. You can't be doing that on every single turn.
You should not. That's why it's critical this summarization is performed asynchronously in the background. Once generated, the summary is persisted so you avoid recomputing it.
And what triggers this compaction?
It can be count-based, hitting a token or turn limit. It can be time-based after a period of user inactivity. Or it can be event-based when the agent detects a task is complete.
Let's pivot from the session, the immediate transactional layer to memory, the long-term knowledge base. What's fascinating here is the architectural requirement for the memory manager to be a specialized, decoupled service. Why not just build it into the agent framework?
Decoupling is essential for scale and for interoperability. By using framework-agnostic data structures, you can have multiple different agents access the same core user facts. This separation also clarifies the distinction between a memory manager and a traditional ROG engine.
How should we think about that difference? They both retrieve information, after all.
They serve completely different masters. A ROG engine is like a research librarian. It handles static, external knowledge documents, PDFs. It makes the agent an expert on general facts about the world.
And the memory manager.
The memory manager is the personal assistant. Its data source is the dynamic conversation log itself. Its goal is to be an expert on the user.
So ROG handles facts about the world. Memory handles personalization about the user.
That's the defining difference.
Let's look at the structure of that personalized memory. Cognitive science distinctions seem to help categorize the data we store.
They do. They give us a framework. You have declarative memory, which is knowing what the facts. This splits into semantic memory, which is general knowledge, and episodic memory, which is specific user facts, like their address. Then you have procedural memory. This is knowing how, the skills and workflows.
And this procedural memory guides the agent's actions.
Yes, by demonstrating the correct sequence to perform a task, like which tool to call in what order.
And organizationally, how do we store this knowledge?
We see a few patterns. You can use collections, which are just pools of natural language memories. You could use a structured user profile, like a contact card for core facts. Or you can maintain a rolling summary, which is a single evolving document summarizing the entire relationship.
These patterns often rely on the storage architecture underneath. How do vector databases contrast with knowledge graphs here?
Vector databases are the standard choice. They store memories as embeddings and are excellent for unstructured natural language facts. Knowledge graphs, on the other hand, store memories as a network of entities and relationships. This is ideal for structured relational queries and understanding complex connections.
And I assume the best systems use both.
The most advanced often use a hybrid approach, combining the structure of graphs with the nuance of vector search.
Let's talk about how these memories are created and scoped.
Creation can be explicit, where a user tells the agent to remember something, or it can be implicit, where the agent infers it from the conversation. Architecturally, the logic can be internal to the framework or rely on an external specialized service.
And what about scope?
The most common is user-level for personalization across all sessions. Session-level memory is just for compacting a specific long conversation. And then application-level or global context represents shared knowledge, often procedural, that's accessible by all users of that application.
Now, for the memory generation pipeline, it's described as an LLM-driven ETL process extract, transform, load.
That's right. Extraction is the first step. It's about targeted filtering. We're asking the LLM what here is meaningful enough to persist. This is guided by system prompts, schemas, or few-shot examples to ensure the LLM extracts only relevant facts.
And after extraction comes consolidation.
Yes. Consolidation is the vital self-editing stage. It integrates new data, preventing the memory from becoming noisy or contradictory.
What specific challenges does consolidation address?
It addresses three things: information duplication, conflicting information like a user's old address, and overall relevance. The manager uses an LLM to decide on a core operation: update, create, or delete an old memory.
For this to be reliable, we need to trust the data. This is where memory provenance comes in.
Exactly. Trustworthiness comes from the source and its age. High-trust sources are things like bootstrapped data from verified and internal systems. User input trust varies. Explicit commands are more trusted than implicit inferences.
And memory from tool outputs.
That's often discouraged because tool outputs can become stale very quickly. Provenance dictates how you resolve conflicts. You prioritize the most trusted or most recent source.
Let's move to retrieval. We have these perfect memories, but we have to retrieve them within a strict, often sub-second latency budget. How do we find the perfect context?
We need advanced strategies, often a blended approach. It combines scores from relevance, so semantic similarity, recency, a time-based score, and importance, which is a score assigned during generation.
And what about timing? I see this distinction between proactive and reactive retrieval.
Proactive retrieval means we load key memories automatically at the start of every single turn. The context is always there.
But the latency cost is constant.
It is, but the results can be aggressively cached. Reactive retrieval, or memory as a tool, lets the agent decide when it needs to query memory.
But if the agent has to decide to query memory, doesn't that require an extra LLM call? Couldn't that mean more latency for the user?
It does require an additional planning step and another LLM call. The trade-off is frequency versus cost. You only pay that latency cost when memory is absolutely required, which might be less often.
Once we have the retrieved memories, how do they placed for inference?
Placement determines influence. You can inject them into the system instructions for high authority, which is great for stable, global contexts like a user profile. Or you can place them directly into the conversation history.
What's the risk there?
The risk is dialogue injection, where the model gets confused and mistakes the memory for part of the actual conversation.
We should briefly touch on procedural memories here, since their use is so different from fact retrieval.
Procedural memory is a reasoning augmentation problem. It's the knowing how. By injecting examples of correct tool call sequences into the context, you get fast online adaptation of the agent's logic.
Which is a huge advantage over the slow, offline process of fine-tuning.
A massive advantage.
To wrap up our technical analysis, let's look at validation. How do we ensure this memory-enabled agent is reliable in production?
We evaluate it across three core dimensions. First, memory generation quality, measuring precision, and recall. Second, memory retrieval performance, this has to be measured by recall, was the right memory in the top results, and latency, which must stay sub-second. And the final, most important test is end-to-end task success. Did memory actually help the agent achieve the correct final output?
And regarding the production architecture itself, we mentioned the asynchronous upload, but why is that decoupling so vital for memory generation?
It is non-negotiable. Memory generation is computationally expensive. If this were blocking the user, the agent would feel incredibly sluggish. It must be a decoupled background process. Production systems also need robust handling of concurrent requests to prevent race conditions when memories are being modified.
And finally, a necessary mention of the continued security risks.
We have to reiterate strict data isolation and PII redaction, but we must also guard against memory poisoning.
Which is when a malicious user tries to corrupt the agent's knowledge base.
Precisely. It involves validating and sanitizing information before it's committed to long-term memory to defend against prompt injection attacks.
So what does this entire architectural stack mean for developers? The critical takeaway is that context engineering, supported by robust session and memory systems, is the required foundation. This is what allows us to move past simple chatbots and build personalized, persistent, and truly reliable LLM agents.
This reliance on LLMs for extraction and consolidation raises an important final question for you to consider, though. Given that the LLM is inherently susceptible to hallucination, how does that risk affect the long-term trustworthiness and accuracy of that consolidated memory, especially when it's used for high-stakes decisions?
That feedback loop between creation and trust is certainly the next complex problem for this architecture to solve. We highly recommend reading the entire white paper, Context Engineering, Sessions, Memory, to gain a complete understanding of these detailed architectural concepts. Thank you for joining us for this technical exploration. We encourage the friends of the show to subscribe for more expert analyses of complex technical material. Have a great day.